Good morning. This is Unit 4 of your paper Microelectronics and Semiconductor Devices. So, in that, Unit 4 is Metal Semiconductor and Semiconductor Heterojunctions. So, the first topic in that unit is about Schottky barrier diode and qualitative characteristics. So, the reference text for Unit 4, that is Metal Semiconductor and Semiconductor Heterojunction, is Semiconductor Physics and Devices Basic Principles by Donald A. Nieman, 4th edition, that is available in the net, so you can download it for your reference. So first let us see what a Schottky barrier diode is. So in 1900, the semiconductor devices that were used was metal semiconductor diode. So this metal semiconductor diode is also called by the name point contact diode, and it is made by touching a metallic whisker to an exposed semiconductor surface. That is how a point contact diode or a metal semiconductor diode is made. Now they are not easily reproduced or mechanically reliable, so they were replaced by PN junctions in 1950s. However, the semiconductor and vacuum technology is now used to fabricate reproducible and reliable metal semiconductor contacts that we all know. Now in this session we are going to consider about metal semiconductor rectifying contact or Schottky barrier diode. In most of the cases, rectifying contacts are made on N-type semiconductor. Okay, so we'll concentrate more on that. Now what are the qualitative characteristics? Characteristics means a few features. Now this is the band diagram for a metal and N-type semiconductor before making contact. It is shown in this figure. Here the reference level that is used is called by the name vacuum level. Now here you can see a denotation 5M. It is actually the metal work function. Okay, that is M denotes metal. So 5M is the metal work function. It is measured in volts. Then 5 is actually semiconductor work function. So 5M is metal work function, whereas 5 is semiconductor work function. Now you can see an expression chi. Chi is nothing but electron affinity. This table, no need of study, you can just go through it. Details some of the work functions of some elements and electron affinity of some semiconductors. Now this one is actually the ideal thermal equilibrium metal semiconductor energy band diagram. It is shown in this figure B. Before contact, you can see that Fermi level in the semiconductor was above the Fermi level in the metal. Now, in order for the Fermi level to become a constant throughout the system, what is happening is that electrons from semiconductor will flow into lower energy state in metal. Then only the Fermi level will become constant throughout the system. Whereas positively charged donor atoms will remain in the semiconductor, thereby creating a space charge region or depletion region, which is marked in this figure. Now another parameter or characteristics is 5B0. It is nothing but ideal barrier height of the semiconductor contact. That is the potential barrier which is seen by the electrons in the metal trying to move into the semiconductor. That is the definition for 5B0. That is ideal barrier height of semiconductor contact. Now this barrier is called by the name Schottky barrier, and that is given by the expression 5B0 is equal to chi m minus 5m minus chi. Okay, so here comes the definition for Schottky barrier. What is Schottky barrier? You have to write this paragraph and this expression. What is 5m? Work function of metal. Chi is electron affinity, which we have already seen. And now on the semiconductor side, you can see a term called VBI. It is nothing but built-in potential barrier. This barrier is seen by the electrons in the conduction band, which is trying to move into the metal, and it is given by the expression, that is built-in potential barrier. The expression is phi VBI, which is nothing but phi B0 minus phi N. Phi B0, what is it? Schottky barrier. Now let us see what happens when a positive voltage is applied. If we apply a positive voltage to the semiconductor with respect to the metal, what happens? Semiconductor to metal barrier height increases, whereas phi B0 or the Schottky barrier will remain constant, and that is the ideal case. This bias condition is termed as reverse bias. Now what happens if a positive voltage is applied to the metal? In the first case we have dealt with what happens when a positive voltage is applied to semiconductor. Now we are considering what happens when a positive voltage is applied to metal with respect to semiconductor. Then the semiconductor to metal barrier will get reduced, whereas that is VBI is reducing, whereas phi B0 will remain constant. So these are some characteristics. All these points are very important when you are asked to write about the qualitative characteristics. Okay. So in this situation, the electrons will flow from semiconductor into metal. Why? Because barrier is reduced. This condition is forward bias. So what is reverse bias and forward bias that you get, and what is the corresponding conditions? Now the energy band diagram for reverse bias and forward bias is shown in figure. Here VR is a magnitude of reverse bias voltage and VA is a magnitude of forward bias voltage. So while you explain those paragraphs, you have to draw this figure also to make your arguments clear. So because all these energy band diagrams versus voltage for a metal semiconductor junction or Schottky junction is very similar to that of our familiar PN junction, right? So because of this similarity, we expect or we assume that the current voltage characteristics of Schottky junction will be similar to that of a PN junction. Okay, now the current mechanism here is due to the flow of majority carrier electrons. In forward bias, barrier seen by electrons in the semiconductor is reduced. So majority carrier, that is electrons, will flow very easily from semiconductor into metal. The forward bias current will be in the direction from metal to semiconductor, and that will be an exponential function of the applied forward bias voltage. Okay, that's all for today. Thank you.